So as we, again, approach here the end of the semester, we're covering chapters 8, 9, and 10. We're almost done with 8. Today will be the last part of 8. And then 9 and 10, we're going to pick some parts and pieces. I'm going to get to you from some of the later chapters, but not like full chapters. I don't even think I assigned really any questions for the check your understanding for you to work on to practice. But I'll map out when we have those in class exactly what I'm looking for. So you can see exactly, oh, got to do this and this and this. It's mostly going to be identification of certain things. And we'll look at some things graphically. If you have a device with you, a computer or a laptop, we're going to be doing a little bit with Desmos today. So have that pulled out and open. So desmos.com, desmos.com. Do some graphing and looking at different things that are going on because math is the study of patterns. So we're going to be looking at patterns and graphing and then talking about how that applies to what we're learning and doing today in class. So most of what we've been doing has been algebraic. There will be some parts like today where we're going to look at graphically what's going on, how they're related one to another as we move through. But first things first. This takes us back, potentially. When do you recall learning like that top one? How old were you what grade were you in, do you think, when you first started doing less thans and greater thans? Any ideas? Seventh grade, possibly. Yeah. You probably learned it at an earlier age, but didn't have the math symbols for it. So you're probably through the math symbols somewhere in middle school. But before that, early elementary, you knew this if you had siblings. Who has more? Right? Because if your brother or sister had more than what you had, of something you wanted, it's unfair. Mom, Dad, it's not fair. But looking at, so when is x greater than 1? And what we typically did, as we learn more about algebra, because that's what this class is about, we did a number line. And on that number line, we put the number 0. And we looked and said, all right, well, and the why 0? Because 0 was the number that I had right here. When I had my variable all by itself, 3 was what we called the boundary point. So I had 0, and that was the boundary point that I had. And then I looked at the symbol, said, okay, greater than. And my 4 symbols for inequalities are greater than, less than. I have greater than or equal to, and I have less than or equal to. So think but don't say out loud. Thinking, what are the difference between those 4 when I go to graph them? When I graph them, how is this different from this, different from this, different from this? All right. So when I'm on a number line, and I'm just going greater than or less than, the difference is these have a closed dot. These have an open dot. So we said, oh, okay, well, I will graph that with an open dot at 0. And then the symbol itself, greater than, means more. X is more. The wide side is more. X is more than 0. More than 0 is over here. Any value in this zone will work for this equation. And then we made this quick little change. So in your notes, jot this down, solve it, graph it. Go. I have a pen. Here you go. If you get that one done, you're like, that was pretty easy, go to the next one. All right, so let's take a look at these. How did you start that, the next one down? You can draw a number line, but before we can put a number on the number line, I need to have this solved for x. Balance, need to move that to the other side, add 3. X less than 3. At that point, the boundary point that I'm going to put on my graph is 3. Open dot or closed dot? Open. Shading left or right? Left. X is less than, smaller than 3. Shading this way, going on to infinity. So again, any number in that zone will be less than 3. So if I pick, and you could, again, not a bad idea, you can pick a number, anything less than 3. If I pick 0, because 0 is less than 3, and I plug it in here. 0 minus 3, negative 3. Is negative 3 less than 0? Yes, it is. We're good. Now what? Solving for x.
You can multiply both sides by 4/1.
Multiply both sides by 4/1. X is less than 0 again. So now we're back to 0. Open dot, shade to the left. The fourth one's a little bit harder because in order to solve for x, you would have to multiply both sides by x, and x times 0 is 0, which we can't do that because then I've lost that x. So instead, here's what I want you to think about. What does it mean to be greater than 0? What type of numbers are greater than 0 when I have a fraction? So again, with a fraction, draw some fractions here. Essentially, there'll be four types here. What type of numbers, when divided, are greater than 0? It's kind of a broad question. All right. What does it mean to be greater than 0? And how did my... Pardon? All right, so negative numbers... Wrong one, wrong tool. There we go. If I have two numbers in a fraction and it ends up being greater than 0, what's another word we use for greater than 0? What's another word we use to mean less than 0? Negative for less than 0, positive for greater than 0. So if I want something that's positive, and I'm dividing two things in a fraction, what makes... So here's what I'm talking about. So I can have things like this. Positive over negative, negative over a positive. I can have a negative over a negative or a positive over a positive. If I want to be greater than 0, so I want to be positive, which of these scenarios will end up with a positive answer? Positive over positive is positive. What else? Negative over a negative is positive. So what I end up with having then is I'm going to have to break this in. Let me see if I can select everything there. There we go. I don't know why it decided to turn on an angle for me. So what I'm going to do is I'm going to say, well, I need x plus 1. So I'm going to start with this one. X plus 1 needs to be less than 0 because that's negative. Subtract 1, x is less than negative 1. So that's the numerator. The denominator is x, so I also need x to be less than 0 because, again, that's what it means to be negative. So when x plus 1 is negative and x is negative, I'll have negative over negative, and that's a positive. On my number line, so I'm going to go ahead and erase, just make it a little bit longer. And here, these are and. What do I mean by and? The numerator has to be negative and the denominator has to be negative. When that happens, then the whole fraction is negative. So I'm going to go to my graph and say, all right, x less than negative 1. Here's negative 1. Open dot shaded to the left. Here, x is less than 0. I go to 0 on the graph, which is above negative 1. I am going to do open dot, and I'm also shading less than to the left. And means, where are they both shaded? So recall the first one I did was x less than negative 1, so I did negative 1 and then shaded left. Then I did 0 and shaded left, and I'm looking to see where did I shade both of them. They were both shaded from here down. Were they both shaded at negative 1? No. So that's an open dot. So I'm going to go ahead and make a little, come on now. Remake that into an open dot. It's an open dot at negative 1. Because at negative 1 it wasn't shaded the first time, but it was the second time. So this green zone, that's where they are both negative. And when they're both negative, I will have a positive number. Now I got to find out where are they both positive. We'll do red. So where are they both positive? So where is x plus 1 greater than 0? That makes it positive. Subtract 1, x is greater than negative 1. That's in the numerator. In the denominator, we want to know where is x greater than 0. I graph them both. Start down here, x greater than 0. So now I'm going to have a red. And I'm going to do it just above the line so we don't see quite so much of the overlap. Going to go all the way up like this. So that is graphing the denominator down here, x greater than 0. The numerator, where is the numerator positive? The numerator is positive, greater than 0, anywhere that x is greater than negative 1. So that means greater than negative 1. So there's negative 1. So I'm going to do negative 1 open dot, greater than negative 1. And in order to be positive, both the numerator and the denominator need to be positive. Positive divided by a positive is a positive. So that's also an and scenario. Where are both of them positive? They are both positive where they're both shaded. So from here all the way up. Which means this entire equation here, when is that greater than 0? It will either be 0 in this shaded region that's green, or in that shaded region that's green. If you're listening to my inflection in my voice and my emphasis, and or mean two different things very specifically in mathematics. And means where they both happen. So they're both shaded. Both shaded. Because, realistically, can I be in this zone where I'm both less than -1 and less than 0? Yes. Up here, in this shaded green region, can I be greater than 0 and greater than -1 at the same time? Sure, like if I'm up here at like 4. 4 is greater than 0, 4 is greater than -1. That works for and. The or is, can I be down here and up here at the same time? No, I can't. I can either be down here or I can be up there. So when I'm finished with this entire thing, what my answer technically is then, is I will be x less than -1, which is this, or, here's the double shaded going up, x is greater than 0. This equation is negative, so this is, we want it to be positive, so it's negative in between here. From -1 to 0, this will be a negative number. Everywhere else, it's a positive value. See if you can make some progress on this one on your own, and then we'll jump back in and do it together. Less than 0 means I want my answer to be, English word, negative, less than 0. So I've got a fraction over here like we had before, either positive over negative, negative over a positive, negative over a negative, positive over a positive. And then thinking which one of these results in a negative value as a fraction. Either this one or this one. Positive over a negative, or negative over a positive. If I start with this one here, in order to be that, I'm going to say, all right, I need my numerator, which is x. I need x to be greater than 0. That's what it means to be positive. In the denominator, I need x minus 4 to be negative, which is less than 0. Down here in the bottom, I add 4. X less than 4. And then I think of my number line. I need x greater than 0, so I go to 0. Open dot, shading this way. I'll keep going further, all the way to the end. In the denominator, I need to go to my boundary point to 4. 4 is right here. It will be an open dot and shaded to the left, x less than, smaller than. 4 is the larger side. It goes this way. And then where are they both shaded? They're both shaded open dot, in between. Then I'll pull this one over. Now I need, in the numerator, negative. So I need x to be negative, which is less than 0. In the denominator, I need the denominator to be positive, which means I need x minus 4 to be greater than 0. In the bottom, I'm going to add 4 to both sides, x greater than 4. Go to my graph. I go to 0. I'm going to have an open dot, and I'm shading left because x is less than. So open dot, shading left. Here, I'm going to go to 4, open dot because it's greater than. X is greater, larger, going to shade to the right. So at 4, open dot, shade to the right. Where are those double shaded? They're not. Which means this can never happen. This can happen, but this can never happen. So the only place that this can be negative, less than 0, is in this green zone down here. That's the only place, because this is not possible. You cannot be both, because we need these both to be true. I need this one to be negative and this one to be positive. In order for the top to be negative, it's here. In order for the bottom to be positive, it's here. And I can't be there at the same time with any of them. That's what makes that not possible. So the final solution is x will be greater than 0 and x is less than 4 in that zone. And now that we've seen that this might not be possible, that means it could also be, I could have a scenario where I go like this, and then we go and we solve all this and realize, yeah, it's never possible for either of them. Which might, and that's also a possibility, where there'd be just no solution. So each individually, I'm looking to see where they overlap. The yellow's overlapped here. Looking for the red, overlap. And the reason why I want overlap is they both have to be true. In order for the fraction to be negative, has to be positive over a negative or negative over a positive. But in order for this to be true, both of these have to be true. And we just showed that they can't both be true at the same time, which is why this way of getting a negative number, not possible. This way of getting a negative number is possible, and it happens in this region right here. And then this would be, again, getting to a larger extension of that. I'll run through one of these, but I'm just going to do one of them as an example. So I need it to be less than 0. Less than 0 is positive over a negative, or negative over a positive. If I want this whole thing to be negative. All right? So when I do that, I'm going to take this over here. I want x plus 2 to be positive, greater than 0. I want x minus 3 to be negative, which is less than 0. I'm going to work this problem up. Subtract 2 from both sides. X greater than negative 2. Work this one down. Add 3 to both sides. X less than 3. Number line. Negative 2. Positive 3 are my two numbers. I need 3, x less than, open dot shaded this way. Here, negative 2, open dot. Oh, wait, no. Less than or equal to. I wrote my equation down. I got to go like this. Since it's equal to, that means it's closed dot. Here at the top, negative 2 is my boundary point. I want x greater than or equal to negative 2. Greater than means more than, so at negative 2 I'm going to shade to the right. Closed dot, greater than is to the right. Less than is to the left. And that's one way, and I can see that the double shaded occurs right here. From 2 to 3, including both 2 and 3. If I take this one over, I need to be negative over a positive. I have x plus 2. Negative means less than or equal to 0. In the denominator, I need x minus 3 to be positive, which means I need it to be greater than or equal to 0. I'll solve this one going up. Subtract 2 from both sides. X is less than or equal to negative 2. This one I'm going to work it down. Add 3 to both sides. X is greater than or equal to 3. I go to 3. I have a closed dot. Greater than means I'm shading to the right. Closed dot. Shading to the right. Up here, negative 2. X is less than negative 2, less than or equal to. So the negative 2 is my boundary point. Less than or equal to means closed dot. X is less than, I shade to the left. I go to negative 2, closed dot, shade to the left. Where do the reds overlap? They don't. So again, this is not possible, which means my final answer is just this green zone here. And that would be x is going to be greater than or equal to negative 2, less than or equal to positive 3. Dealing with positives and negatives. This probably looks familiar. I think this was on one of the exams, first one or the second one. Probably the second one, because it was more about solving. So in order to solve, we need to, and it's set equal to 0, my first thought is, should always be, can it be factored? First step of factoring is the greatest common factor. They do not have a greatest common factor. Then I need to think, is it a special form? It is not a special form. The only special form we've really spent time on is this one, x squared minus 9, or x squared minus 16, or x squared minus 81, where it's x squared minus another number that's squared. I've also not really done much with p to the 4th versus p squared. But what I can do, because, let me just write it above here, ax squared plus bx plus c has been the form and format that we've mostly worked with, where the first term is squared, the second term is just a single power, and the third term is a constant. In this scenario, the first term is something squared. It is p squared squared. The second one is something to a first power, technically. It's 3p squared. I'm going to get rid of the parentheses, though. Go like that. If this was x, this is x squared. This is p squared, so this is p squared squared. If you want, you can do what's called just a substitution. Let's let x equal p squared. If I do that, then I will have x squared minus 3x minus 4 equals 0. And now it looks a lot like the problems that we have done, or it should. If I do the full x box method, oops, sorry about that. Come back down here. There we go. If I do, yeah, we could do the full x box method, or really when this coefficient is 1, I am thinking two numbers that multiply to negative 4. 4 and negative 1, 2 and negative 2, negative 4, positive 1. Those are all the numbers that multiply to negative 4. Which pair adds to negative 3? Yep, this pair right there. Which means this will factor into x minus 4 and x plus 1. Equals 0. And as we've done, and we will do several more times, even on the final exam, I have two things that multiply to give me 0. In order to multiply to get 0, either, oh, come on now. Why won't not let me select everything? There we go. I want my p squared stay over there. Either this one, x minus 4 equals 0, or this one, x plus 1 equals 0. But it's not just x. It's actually p squared. So I'm going to rewrite p squared minus 4 equals 0. P squared plus 1 equals 0. This is a special form of the quadratic. It's a difference of squares, two things that are squared. This is x squared, that's 3 squared. This was x squared, and that's 4 squared. This is x squared, that's 9 squared. This is p squared and 2 squared. P plus 2, p minus 2. It would be my hope that by this point in the class, that anytime you see a difference of squares, you automatically hits you in the head and goes, ah, yes, difference of squares, p plus p minus, p plus p minus, or x plus x minus. This is not a special form, so we'll just continue to solve this one algebraically. But before I do, I go back over here and say, just like I did up above, I have two things that are multiplying to be 0. What makes this 0? P equals negative 2. What makes this 0? What number minus 2 is 0? Well, that's p equals 2. And then back with the other equation, subtract 1 from both sides, p squared equals negative 1. The inverse of squaring, to get my p by myself, is square rooting. P equals the square root of plus or minus negative 1, which is the imaginary number I. Square root of a negative 1 is I. So I have 4 solutions, because it's p to the 4th. 2 of them are real numbers. The other 2 are imaginary numbers. So if I were to actually graph this, it would intersect the x-axis twice at 2 and negative 2. Then we have another one that looks like this, and we go, oh, that I don't like fractions. Most people don't. But I look to see if I go back to my ax squared plus bx plus c, is that in a similar form? Is this variable, when I square it, this variable? And it actually is. If I were to take x to the 1/3 times x to the 1/3, that's squaring when you multiply it by itself, When I have same bases and multiply, we add those exponents. So that equals x to the 2/3. So this time I'm going to let, because we did it the other way, let p equal x to the 1/3. If I do that, then this is p squared minus 5p plus 6 equals 0. When the leading coefficient is 1, shortcut to factoring is I just list all the numbers that multiply to 6. 2 times 3, 1 times 6, negative 2 times negative 3, negative 1 times negative 6. Ooh, that's a 16. Times negative 6. Do any of these pairs add to negative 5? Negative 2 and negative 3. So this would factor into p minus 3 and p minus 2 equals 0. I have two things that multiply to 0, which means one of them has to be 0. So either p minus 3 equals 0 or p minus 2 equals 0. But it's not just p, it's actually x to the 1/3 minus 3 equals 0 or x to the 1/3 minus 2 equals 0. Because that's what p was equal to up here. So once I got it figured out for p, substitute that in. Solving for x, add 3 to both sides. X to the 1/3 equals 3. Or, over here we add 2 to both sides. X to the 1/3 equals 2. And then we have to figure out or try to remember, how do we get rid of fractional exponents? Sometimes it's a matter of remembering what is a fractional exponent. It won't let me. All right, we'll just do this. X to the 1/3 is the same as the cube root of x. And maybe that helps. How do I get rid of a cube root? Well, let's go back. How do I get rid of a square root? What's the inverse of square rooting? Dividing is the inverse of multiplying. Inverse of square rooting would be squaring. Just like the inverse of squaring, which we've done already, is square rooting. So now we've got cube root. What do you think the inverse of cube rooting will be? Cubing, correct. So I'm going to cube both sides of each equation. When I do that, the cube and the cube root are inverse operations, leaving me just x, and then 3 cubed is 27. 3 times 3 times 3. Or cube root cubed, inverse operations, left with x, equals 2 cubed, which is 2 times 2 times 2, which is 8. If you use an old school calculator, I've been asked this many times, how do I do multiple powers? Depends on what type you have. If you have just a regular scientific calculator and I wanted to find, let's say it's a different number, 5 cubed, in my calculator I would type 5, then there is a button that's x to the y power, and then I would type 3. Because what you're telling your calculator is 5 is the base. Of that, I'm going to do x to the y, which is something to a different power, and my y is 3. And then it would kick out the answer of 125. If you're on a graphing calculator, it's 5, then you hit the caret button, and then 3. So that's 5 to the third power. If I had to do, while I'm on it here, let's just do this, shrink that up and move it up more. If I had to do, let's say, the 5th root of something, and we had to find it as a decimal, because this would not be an actual whole number, how would I do that? Typically, well, there's a couple different ways. I would rewrite it as 125 to the 1/5 power. That's what the 5th root is. It's the 1/5 power. On my calculator, I would do, if I have a regular scientific calculator, 125, comma, x to the y. And then the next thing, now you don't actually type in the commas, right? You type in 125, you hit the x to the y. Then I do parentheses, 1 divided by 5 end parentheses. So that would be taking 125 to the 1/5. If you wanted to, or if you knew it, you could convert 1/5 into a decimal, which is 0.2. Then I could do 125, then I would hit x to the y key, then I would type 0.2 and hit enter. Get me to the same place. All right, jumping back a bit. Fractions and solving equations. Go ahead and give these a try. So for the first one, I'm not sure how you went about doing it. I like shortcuts. I like to ease things off, and I don't like to work with fractions if I don't have to. I notice, first off, all 3 fractions have the same denominator. And if they're going to be equal and the denominators are same, that means I can just write the numerators as its own individual equation, and I don't have to deal with the fractions at all. So when they have the same denominator, I can just solve it with just the numerators. They're all 3. So I have 1 minus 2, which is -1, equals x. Could you combine the fractions? Sure, 1/3 minus 2/3 is -1/3 equals x over 3. -1/3 equals x over 3. Then you could do cross multiply and divide, or you can multiply both sides by 3. Either way, you're going to get to the same answer. In this second equation, I'm noticing my denominators are different. If I can make them all the same denominator, then I can set the numerators equal. My common denominator will be 15. In order to get there, I multiply the first one by 5 over 5, which will give me 5 over 15. I multiply this second fraction by 3 over 3, multiplying it by 1, doesn't change it, minus 6 over 15 equals, and this third fraction I multiply by 5 over 5, so that will be 5x over 15. All the denominators are the same, which means if those are going to be equal, if the denominators are same, that means my numerators have to be the same in order to be equal. 5 minus 6 equals 5x. So yes, I'm essentially saying you can ignore the denominator at that point, once they're all the same. -1 equals 5x. Divide by 5, x equals -1/5. Are all my denominators the same? No, they are not. To get them to the same, it looks like I need, this is 3x, that's 3, that's 3. These both need an x. So if I multiply this by x over x is 1. multiply this one by x over x. I will then have, the first one stays as is, as 1 over 3x, minus, and now here I'm going to multiply these, so 2 times x and 3 times x, 2x over 3x. My equal sign stays where it is. In the numerator, x times x, x squared. In the denominator, 3 times x, which is 3x. Now I have all denominators the same, which means I can set the numerators equal to one another. 1 minus 2x equals x squared. Guess what? It's a quadratic, which we've been doing. Sometimes it feels ad nauseum, like way too much makes you nauseated, or just quadratics themselves do, but I love them. They're also one of the biggest root issues that we deal with in Algebra 2 that spawns into what you're going to take in pre-calc, even in stats. So quadratic, to solve it, we set it equal to 0. I like my x squared to be positive. It's easier that way. So I'm going to move everything to the right-hand side. Add 2x and subtract 1 to that side over here. Those are equal, so I'm going to add 2x and subtract 1 from that side. I'll have 0 equals x squared plus 2x minus 1. And then I think, what numbers multiply to negative 1? Positive 1 and negative 1. Do they add to 2? No. Darn it, can't use the quadratic formula this time, or can't use factoring this time. I will have to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Substituting values in, ax squared plus bx plus c. So the the b value is 2, so negative b is negative 2, plus or minus. The b value is 2, so it's 2 squared. 2 squared is 4. Minus 4 times a, the a value is 1. That's the number in front of the x squared. The c value is negative 1. All over 2 times a, and a is 1. Start simplifying. X equals negative 2 plus or minus the square root of 4. And then I have negative 4 times 1 times negative 1. Negative times negative is a positive. 4 times 1 plus 4. All over 2 times 1, which is 2. X equals negative 2 plus or minus the square root of 8 over 2. Going to take that square root of 8 and do simplified radical form. Are there two numbers that go into 8, one of which I know the square root of? Two times 4 is 8. So square root of 2 times square root of 4 is square root of 8. I know the square root of 4. It is 2. I do not know the square root of 2. 2 is a prime number. It stays as is. So the square root of 8 can be rewritten as 2 times the square root of 2. So over here I have x equals negative 2 plus or minus 2 square root of 2 all over 2. That's a whole bunch of 2's. Always looking, can this reduce? Do all parts of the fraction have anything in common? Yes, they do. Negative 2 can be divided by 2. 2 can be divided by 2. Final answer, x equals negative 1 plus or minus the square root of 2. Long process to get to, this one here. to get to a solution on this. But it involves quadratics, quadratic formula. A problem like this takes into a lot of things into account. Rationalizing the denominator, quadratics, quadratic formula, simplified radical form. Lots of aspects that go into a single problem like this. When looking at exam type problems, this would be I would, in a teacher educator point of view, would be a good one because it capitalizes on a lot of different topics. Same idea. We need the denominators to all be the same. X times x minus 2. This is just x. This is just x minus 2. This is where I want to get to for my final answer, my final denominator, which means this needs to be multiplied by x over x. The middle one, it's going to kind of be messy here in the middle, needs to be multiplied by x minus 2 over x minus 2. So then I'll have in the numerator 3x times x, which is 3x squared, over x times x minus 2. X times 3x, 3x squared, x times, there's my x minus 2. Minus, up here in the numerator, I have x plus 1 times x minus 2. In the denominator, x times x minus 2. The one on the right had that all as it was to start with. All the numerators all the denominators are the same, which means I can just strip them away and have 3x squared minus x plus 1, x minus 2 equals 6. It's a quadratic because I know this is x squared, which means actually I need to FOIL this out. Get everything minus first x squared, outside negative 2x, inside's positive 1x, last's negative 2 equals 6. The middle two terms combine, negative 2x plus an x is minus x. And then in terms of trying to skip steps so I save space, this negative then needs to distribute to every term. I'll have 3x squared minus an x squared plus x minus a negative x, that's plus x, and then minus a negative 2 is positive 2 equals 6. X squared plus x plus 2 equals 6. To solve a quadratic, I set it equal to 0. 2x squared plus x minus 6 equals 0.
Wouldn't it be minus 4?
Minus 4. Two minus 6 is negative 4. Could do completing the square, could do the quadratic formula. You could try factoring and find out that you can't factor it, not easily. So instead you'd use the quadratic formula, which we just did one before that, so I'm not going to do it again. We'll move on to the next question. Solving. Square root of x. Inverse of square rooting is squaring. X equals 9. Next one, we just have a minor step in the process. First, you have to get the square root by itself, so I have to add 3 to both sides. I'll then have square root of x equals 3, which we just did. Square both sides, x equals 9. Another just minor step up from that. Again, first thing when solving for square roots is you got to get the square root all by itself. To get the square root by itself, we add 4. Square root of x equals 6. Inverse of square rooting is squaring. X equals 36. So all 3 of those, just quick and easy remembering. First thing first, always have to have the square root all by itself on the left or the right, one side or the other. All the other things on the other side. And then we add a layer. All right, so now what? Need to subtract 5. Both sides, I'll have the square root of x minus 1 equals negative 3. Inverse, now everything on the left is square rooted. Inverse of square rooting is squaring. X minus 1 equals 9. Be careful. If you type into many calculators, even your graphing calculator, if I type in negative 3 and then hit the squared button, it will tell you negative 9 for an answer. Your calculator is wrong. It just doesn't know order of operations very well. So be cautious to not always trust your calculator with that, especially with negatives. Negative 3 times negative 3 is positive 9. Negative times negative is a positive. Add 1. X equals 10. Add another layer to it. Now we add 2 to both sides to get the square root all by itself. Inverse of square rooting is squaring. Over here we square the whole thing. On the left I have x. On the right I have x plus 2 times x plus 2. Squaring means times itself. Do you need to separate it out like that? Yes. If you don't, people make bad mistakes. The bad mistake is they say, well, that's x squared plus 4, which it is not. X times x, x squared. We'll do x times 2, 2x, 2 times x, 2x, 2 times 2 plus 4. X equals x squared plus 4x plus 4. Subtract an x from both sides because it's a quadratic and we want it to be set equal to 0. I could look at this first and say numbers that multiply to 4 are 2 and 2, 1 and 4, negative 2, negative 1, negative 4. Do any of those pairs add to positive 3? That adds to 4, that adds to 5, that adds to negative 4, negative 5. No, they don't. There's not an easy way to factor it. It would be a quadratic formula equation again, which again, we've done a couple times already today. I'm not going to do it again, but getting to that place of setting it up. Again, steps are, with a square root, move everything that's not a square root to the other side. Then I can square because then the inverse of square rooting is squaring, leaving me only what's inside. On this side now it expands out into a quadratic. We then solve that quadratic using the quadratic formula. Sharing multiple concepts in the same steps. Similar idea. Add 2. Subtract x from both sides. Common mistake people make is they forget that that negative is actually attached to the square root. So negative square root of 19 minus 2x equals negative x plus 2. It's a plus up there. That negative then, I want to get rid of the negative. So I'm either going to divide everything by a negative number, multiply, which is usually what I do, if I multiply everything by -1, I'll have square root of 19 minus 2x equaling x minus 2. Got the square root all by itself. In your head, you're already saying, yes, we've done this. We square. We square. 19 minus 2x equals x minus 2 times x minus 2, which is x squared minus 4x plus 4. I did the FOIL already. Combine those middle terms. 19 minus 2x on the left. Need to set it equal to 0. 0 equals x squared. I add a 2x to both sides, so it'll be minus 2x. I subtract 19 from both sides, negative 15. And then I list numbers that multiply to negative 15. Do any of those pairs add to negative 2? Negative 5 and positive 3. The middle term is negative, so that means I know that in these, the larger value has to be negative. So that's plus 3 equals 0. X will either be 5 or x will be negative 3. Either this has to be 0, because 0 times anything is 0, or this one has to be 0, because 0 times anything here is also 0. 5 makes this 0. Negative 3 makes this one 0. Those are my two solutions. We're gonna skip that one. This is where I said have Desmos out. I want you to graph these. Graph x squared, then x squared minus 1, all in the same graph. Then x squared minus 4, then x squared plus 5. Do all of those on the same graph, and then tell me what you notice. What generalized statement can you make after you graph them? Yes, there is. Yeah, there should be a comma. So we're going to take something that's in general form, which is this, and we're going to put it into vertex form. And we're going to do it by completing the square. So first off, we're going to do completing the square, which is something we've done. Maybe not enough for you to go, I'm super confident in that, but we're going to give it a try. So completing the square starts by moving the constant to the other side. So I added 12 to both sides to move the constant over. So when I have only my x variables on one side, now I can actually do the step that is called completing the square. The completing the square is I take half of the b term, square it, and add it to both sides. So what that means is I take half of, so I'm going to say plus over here. Let me do it in the white so it stays consistent. So I'm going to do plus half of the b term, half of negative 4, square it. Whatever I do to the left side, I have to do to the right side. So I'm going to take half of negative 4 and square it. I'm missing a set of parentheses there. There we go. On the right side, I'm going to leave it as x squared minus 4x plus, that's negative 2 squared. This is negative 2. 1/2 times negative 4 is negative 2. And I'm going to leave it like that on purpose. On the other side, though, I'm going to simplify. It'll be y plus 12 plus, and you say, all right, well, what is, this is the same thing. What is negative 2 squared? Negative 2 times negative 2 is positive 4. So on the left, I'll have y plus 16 equals. On the right side, this factors into x minus 2 squared. Completing the square makes it so that when I factor this, what two numbers multiply to negative, sorry, over here would be the positive 4. What two numbers multiply to positive 4 that add to negative 4? And that's negative 2 and negative 2. I don't have to go that far. I can just recall that whatever the half the b is, half of b, half of negative 4, that's my number in my parenthesis. This and this are almost the same. And I'm actually going to leave it in this form right here. I prefer this. Some books will say this is vertex form. I prefer this one as vertex form. You can do either one. What do I mean by vertex form? What makes that 0? X is 2. If x is 2, it makes that 0. What makes this 0? Y is negative 16. Negative 16 plus 16. So negative 16. In a graph, xy, 2, and we'll call this negative 16. At this point right here, 2, negative 16, that is the vertex of the parabola that we're graphing. What we've been doing all along is saying, well, what makes this 0? 0 equals x squared minus 4x minus 12. What two numbers multiply to negative 12? I've got negative 6, positive 2, negative 4, positive 3, negative 1, positive 12, and then back and forth. This pair, negative 6, 2, multiplies to negative 12, adds to negative 4. 0 equals x minus 6, x plus 2. What makes this 0? X equals 6. What makes that 0? X equals negative 2. On my graph, negative 2 is right there because I said x equals negative 2. 6 is over here. 1, 2, 3, 4, 5, 6. I have a parabola. That's really a terribly drawn parabola over the top of everything. But I've been finding these zeros using factoring to find out where it crosses the x-axis. I'm going to use completing the square to find the vertex. I'll do another one now. Move the constants to the left. Y minus 3 equals negative 4x squared plus 4x. Before I can do completing the square, I need the first term. Has to be 1. To make this 1, I divide by negative 4. But if I do anything to one thing, I do it to everything. So then I'll have negative y over 4. This is negative over negative, so that's plus 3/4. Don't worry about the fractions. We'll deal with them later. X squared minus x. Completing the square is I take half of b, square it. I'm going to add half of negative 1 squared. Over here, I'm going to take half of negative 1, square it. Negative y over 4 plus 3/4. Let's see. Half of negative 1 is negative 1/2. Negative 1/2 times negative 1/2 is positive 1/4. On the right side, I'm going to have x squared minus x plus, and I'm just going to leave this as negative 1/2 squared. The right side factors into x minus 1/2. Half of b, half of negative 1, negative 1/2 squared. This will equal negative y plus, negative y over 4 plus 1. In order for it to be in vertex form, I need the y to just be a y. It can't be y over 4, or in this case, negative 4. I multiply everything by negative 4. Negative times negative is a positive. The 4's reduce, leaves me with y. Negative 4 times 1 is negative 4. So y minus 4. Negative 4 times that whole parenthesis set, x minus 1/2 squared. What makes this 0? What makes this 0? The value that makes x, the value of x that makes this 0 is the x coordinate of my vertex. The value that makes this 0 is the value of the y coordinate of my vertex. That's the vertex of the parabola. Y plus 3 equals x squared minus 2x. Add half of b, half of 2 squared. Here I'm going to add half of 2 squared. Half of 2 is 1. Y plus 4 equals x minus 1 squared. The vertex is 1, because 1 makes the x 0. The y value is negative 4. That's what makes this 0. That was quick. We're going to skip that one and that one. Those are the check your understanding problems. If you've been studying and prepping and doing all the check your understanding problems, you will have noticed, hopefully, that these problems are often the problems that occur on exams. Not all of them, because I can't put all of them on there. And then I tend to go through answers in the class, and I bring up old questions that we've done, probably because they might appear again. Or if you're looking at studying and retake an exam, you can use that too. It's 9:31. I went a little long. See you on Tuesday.